which is the example 3. I think we already solved this and discussed how we can find all the dimensions, if you remember, right? Did we finish the solution for this problem?
No, we didn't. We finished example 1 and 2 just.
I think we did that before.
Yes, doctor, I think we did.
Yeah, we did. We did.
Calculate the free resistance and the right side itself.
Yeah, I requested from you guys to solve it again at home, so that you make sure to know exactly how to do the calculations. But I will go through it just very quickly, make sure that we are all on the same page. It's an easy one. Why? Because we need just to represent the magnetic circuit as electric circuit. And after that, find all the reluctances that we have in the circuit. And we said that the optimal number of reluctances, as shown here, will be 2. Reluctance 1 representing all these 3 legs. Why we are representing all of these 3 legs in one reluctance? Because they have the same material and they have the same cross-sectional area, right? And the second one, R2, will be this leg here, or this side. Why this side is alone? Because the cross-sectional area is different than the cross-sectional area of the remaining 3 legs. How do we know this? It's from the width of the leg itself, or side. Here it's 10. Here it's 15. Here it's 15 also. Here it's 15. So if you cut this magnetic core, you will find basically that the cross-sectional area here will be 15 by 10, where 10 is the depth of the core. If you cut also this, you will see that it's the same, but this one is different. The cross-sectional area will be 10 multiplied by 10. So that's why we represent this as another reluctance. You can represent this with 4 reluctances, that's fine. But the optimum number is 2. Once we do this, finding the flux will be easy because we can find first the if we already have the number of turns, we have the current. We already now have R1 and R2. So we divide this F by the combination of R1 and R2, we can get the flux. So any question regarding this solution? We did that before last time, but do you have any question regarding this example? Okay. So now we will proceed and we will go through different examples also today and discuss how we can solve them. And maybe we experiment few different ideas through these examples. Example 4, this is where we have magnetic core with a relative permeability of 4,000. So mu r is equal 4,000. Assuming a fringing coefficient of 1.05. Do you remember the fringing coefficient? Or the fringing effect?
The increasing of distance or the
cross-sectional area. Yes.
Yeah.
In the air gap.
Yes, for the air gap, now what we are saying here is that the cross-sectional area is more because we have this effect. So the air gap effective cross-sectional area is more than the core cross-sectional area by 5%, which is 1.05. Find the flux density. Density, is it B or H?
B.
In the air gap, so whatever we have density in air gap, we need to find it. If the current is 0.6. So from the left side, we know that mu r is 4,000. 1.05 is fringing coefficient. Bg is the air gap that we need, the air gap of flux density. We need to find it. And the current is 0.6. Let's go to the right side and see exactly the magnetic core. What do we have here in the magnetic core? Notice the dimensions here, because every time you might have different set of data or dimensions, etc. So you need to be able to read whatever you have in front of you. So what do we know from the figure? The number of turns 400. It's given here, right? It's not given in the written problem. It's given in the figure. What else? We know the air gap dimension.
Doctor, excuse me, what is the given in the figure?
Again?
What is the given in the figure?
First, yeah, it's the number of turns 400. We have the whole magnetic core in front of us. We have two main components, the core, which is the material, and also air gap. So yes, we can represent the electric circuit or the equivalent circuit as the source, which is the coil, one reluctance representing the core material, one reluctance representing the air gap. Both of them or all of them, they are connected in series. Regarding dimensions, cross-sectional area is given 12 centimeters square. So we don't have to worry about cross-sectional area for the core. It's already given. We don't need to calculate it similar to example 3. The length, the average length for the core is given also, 40 centimeters. The air gap length is given, which is 0.05 centimeter. This is basically all what we need. So in terms of dimensions, it's much easier than the previous example, right? We don't need to calculate now the average length or the area. All of them, they are given. So the question now is how we solve this circuit. We need to find the density at air gap, which is B. So how we do this? Think about this for a second.
The fringing coefficient.
Well, the fringing coefficient is there, we know it, but how we can reach BG?
We have to find the flux.
We need to find the flux. Good.
And the area of fringing of the air.
The cross-sectional area, yes. Divided by the cross-sectional
Already
area.
there. Yes, that's correct. Good.
Divided by the volume.
We can find the flux from the relation F over R. Then
Okay.
we should calculate the density.
Okay, good. All of these answers, they are correct because we'll need to do all of this. First of all, let's basically clarify what do we know about the circuit here. We know this. We can calculate this because N already given 400, I is already given 0.6, right? So we know what is F for the whole circuit. The question, can we find RC?
Yes.
Yes, we can find RC. Why? Because RC will be, if you remember the equation, RC will be
LC over
LC,
mu N.
which is 0.4. Why 0.4? Because we need to change it to be in meter, divided by mu R, mu naught. Mu R is given also, 4,000. Multiply by 4 by 10 to the power minus 7, which is constant. Multiply by A, the cross-sectional area of the core, which is 12. So yes, we can find RC. Can we find RG for the air gap or RA? Yes, similarly, it's 0.05, the length of the air core, air gap, 10 to the power minus 2, divided by 4 pi, 10 to the power minus 7, divided by A, which is again 12 centimeter. Is it correct?
No. We need to multiply by the coefficient of fringing.
Good point. The area, the effective area will be this, the whole this, for the air gap, because we have this fringing coefficient, 1.05. So you need, every time you use the area of the air gap, you need to multiply by 1.05. And this is correct, yes. Do we have mu R, relative permeability for this air gap? No.
It's 1.
It's 1. So no need to include basically mu R. So we have this, we have this, and we have this. What we can find, yes, that's correct. We can find the flux, which is similar to the previous example. So this is 1, this is 2, this is 3. 4 will be flux is equal to F divided by RC plus how many fluxes we have in this circuit? Only one. Only one. Similar to the current in electric circuit. What's next?
Density.
Divided
flux.
by area.
Yes, there is an equation for B. I'm gonna write it here, which is step 5. Now, B will be flux divided by area for the gap. Flux, we already have flux. Area will be what? Again, it's 12, 10 to the power minus 4 multiplied by, sorry, 1.05. Okay? That's it. This is the solution here. 1, we find F. 2, we find the reluctance for the core. 3, we find the reluctance for the air gap. 4, we find the flux. 5, we find the density at the air gap. So any question regarding this?
Doctor, when do we have to find the cross-sectional area for the air gap? Is it always the same as the air cross-sectional area of the core?
Yes, but except that we have what we call the fringing coefficient here. Fringing coefficient, if you remember, it was the concept that the cross-sectional area of the air is larger than the cross-sectional area for the core by a percentage. How much percentage? It's given as the coefficient here. For example, here it means that this area is 1.05 multiplied by core area.
No, I mean, we don't have fringing coefficient.
It's mentioned in the if we don't have, yes, it's the same. If we don't have, it's the same. But in this example, we are assuming that we have fringing coefficient of 1.05. Okay?
Okay.
Any other question? So yes, this is the solution. You have it in the slides. And this is how we find, for example, the RC, RG, flux, and after that, the density. Example 5. Using magnetic circuit concept, analyze the toroid coil shown in figure 1. The magnetic circuit is analogous to electric circuit switching. Okay, so we don't have basically numerical problem here, just a small discussion about the circuit. Nothing also new, but here it's a donut shape. And this is just to explain to you that it's not always rectangular shape that you might deal with in magnetic circuits. This is a donut shape. So the main difference here will be in the cross-sectional area and the average length, right? So if you cut basically this magnetic core, what will be the shape that you will see?
Rectangular.
It's circle. Okay? As I said, it's like donut. So if you cut this, it will be circle. So when you, for example, analyze the magnetic core and you need to find the cross-sectional area, it's going to be pi r square, right?
The r will be r outer minus r inner, of course, to the power of 2.
Divided by 2, yes. For example, r, which is this basically radius, it will be the outer radius minus the inner divided by 2. You see this? So this is r divided by 2. Which is basically the radius of the circle, yes. So either it is given, or knowing all of these dimensions, you can find it basically from the difference, because the difference will give you 2r, and you need r for the area to find, which is pi r square. The average length, how we can find the average length, which is this dashed circle also. Well, if it is given
فكرة هذه مع rectangle
2 pi r.
Yep.
Right? If it is given, if this r is given.
Parameter, right?
Yes.
Yes. If you are given the outer and the inner, again it's similar. If you are given this and this, what you need to do is basically finding this. What will be r if you are given the outer and the inner? R will be this plus this divided by 2, which is the average, right? No, the cross sectional area. cross sectional يعني كأنك جايب سكين وتقطع الجزء هذا هنا. We need to find the radius. مثل ما قلت لك انت تخيل الشيب هو توريود، الشيب دونات. فانت لما تقطع الدونات هذا بيصير عندك سيركل اريا. طيب ايش الراديوس حق السيركل اللي قطعتها؟ ايش الراديوس؟ الراديوس انت ممكن يعطى لك can be given, or from the outer and the inner radius. معناها انت اذا عندك الاوتر وعندك الانر الفرق بينهم بيكون ايش؟ بيكون the whole distance here, which is not the radius.
الفرق بينهم الدياميتر راح يكون حق الكروس سكشن دكتور.
Yes basically. من وين تشتري الدونت؟ It's not a circle, as I mentioned. It's a toroid. يعني it's basically circular shape, cylindrical shape خلينا نقول. اوكي. فانا فاهم انه دانكن دونت مثلا شويه الدونت حقتهم غريبه، بس خلينا نقول كريسبي كريم دونت. اوكي. لا true يعني I understand exactly your point, but when I said donut shape I meant اللي هو fully circular cylindrical خلينا نقول donut. Any other questions? So basically here I'm just highlighting that you need to be careful about the cross-sectional area and also the average length for different shapes. Usually the typical shape for magnetic core is rectangular shape, but in case you have different shapes, be careful about how to find the cross-sectional area. So you can see it here, which is basically how we find the reluctance by finding also the average length and cross-sectional area. Example 6. Consider the magnetic core with an air gap as shown in figure 3. The core material has a relative permeability of 6,000. So this is the first piece of information. Mu r is 6,000. And the rectangular cross-sectional area 2 by 3. The coil height is 500. Determine the current required to establish flux density of 0.25 in the air gap. So it's again, it's similar to the example 4, where we had to find the density in the air gap knowing the current. Now we need to find the current knowing the density. It's exactly the opposite. And again, we have air gap, we have the dimensions. So it's a little bit more difficult now because now we need to deal with dimensions, but representation wise it's the same. Procedure is the same because we know we need to find the current knowing that BG is given. So it's the opposite now. Since we know this BG, we can find flux. Once we find the flux, we can find current. Okay? So let's start one by one.
بس دكتور الاريا هنا راح تكون يونيفورم.
ايش؟
الاريا راح تكون نفس الشيء ثابته.
I don't know. We will come to the area. يعني yes, we have one R core, and if you can see here the
2 centimeter.
It's 2 here. It's 2 here. It's 2 here, and here also 2. So the core cross-sectional area is uniform. Yes. Okay. So we need, first of all, we need to find what is R gap and R core. So this is the first step. Let's start with the R gap because it's the easiest one. R gap will be average length of the gap, which is 0.5 multiplied by 10 to the power minus 2 divided by 4 pi. Do we have fringing coefficient? No.
No.
What's the area? The area is as given 2 by 3. Multiply by 10 to the power minus 4. Okay? So is it clear?
دقيقة دكتور آخر شيء حقت الفرنجنج كوفيشنت.
There is no fringing coefficient here, so we don't have to multiply the area by any number.
Yep.
Let's come to RC. RC will be the average length divided by mu divided by A. But here we need to find what is the average length and the mu and the area, because they are not directly given. So what would be the average length, LC? Well, first of all, we need to find, let's try with 1 and see exactly if we just need to multiply it later or not. Let's try to find the average length here. Do you remember how we can calculate this?
Yes.
It's the outer
Yes, it's
length
8 plus
plus the inner length
divided by 2.
What is the inner length here?
4.
Why 4? Because it's 8 minus 2 minus this, right?
Yes.
Divided by 2.
It will be 6.
6. What about here?
Same.
It is the same.
What about here?
The same also.
What about here?
Same.
6.
Why I subtracted 0.5?
Because the length
Because the gap is 0.5.
Yes, we need to exclude the gap from the average length of the right side. So on this one, if we don't have air gap, it's the same as the other 4 legs. That's why I multiplied by 4 here. But since we have air gap, we just need to remove this air gap length from the length of this leg. That's why I subtracted 0.5. Is it clear for everyone?
دكتور بس انت قسمت على ايش بالضبط؟ ما اشوف اللي تحت اخر شيء في نفس اللي قبل شوي في ال LC. 8 plus 4 divided by how much?
2. مو واضح لكم؟ اوكي 2. So this is 23.5 10 to the power minus 2. Is it clear?
Yes.
It's divided by 4 by 10 to the power minus 7. 6,000. And the area, what is the area? The area is given 6 10 to the power minus 4. Is it clear how we can find RC? So RG will be number 1. RC is number 2. Do you have any question regarding this?
No, it's clear.
So now we know what is RG. We know the R core. BG is given. I is given. Sorry, we need to find I. Yes, we need to find I. N is given. So what to do? Can we find the flux? Yes, and this is step number 3. Flux will be the density at the air gap multiplied by the area at the air gap. Density is given, it's 0.25, multiplied by the area, which is 6 10 to the power minus 4. Clear?
Yes.
What is step number 4?
Find the current.
Find the current. Before we find the current, we can find what is F, which is basically, yeah, same as finding the current. So 4 will be F is equal flux multiplied by what?
Total reluctance.
Total reluctance, good, which is RC plus RG. Do we have this? Yes, we have this. We already have the reluctance for the gap, for the core, and the flux. 5, I will be F divided by N. Okay? Of course, you can do 5 and 4, but again, just for the sake of explanation, I am putting it as extra step. Any question regarding this?
No, it's clear.
Okay. Reluctance, where? هذه. لا لا لا. But all of them, they have the same cross-sectional area, which is 2 by 3. So this one. لا 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 فاهم عليك. انت قاعد تقول بما ان في اير جاب هنا ليش ما نفصلهم كذا؟ لا لا ابدا. Just add all of them. You can do this, but again, it's going to be more complicated to find what's the average length if you do this. So you just add all of them together, as I said. Okay. Any other questions? Again, this is the solution. You have it in the slides, so just go through it later. Example 7, we're not going to solve this, but again, we're just going to discuss what should we do, or basically how we represent this circuit. It's not an easy circuit to deal with. I don't know if you have the solution here. No solution. But again, no time actually to go through the whole solution. What do you have? We have the circuit and all the dimensions, and you need to find flux and the flux density in each leg of the magnetic core. We have coil in the middle. We have air gap, and we are neglecting many things here. So the circuit will be super easy. What we are neglecting the leakage iron reluctance. This is important. What does that mean? If we are neglecting the material reluctance, it means that there is no need to represent the core, only the air gap, right? And there is no fringing in the air gap. So how many reluctances we have in this circuit?
Two.
So we have one reluctance to the left, source in the middle, another reluctance to the right.
Doctor, what do you mean we have one resistor because two reluctance because if we have neglecting leakage.
No, but the air gap, we have 2 air gaps. Okay, and we are neglecting the core, the reluctance for the core. So we only have air gap 1 and air gap 2.
Why did we neglect the reluctance of the core?
We didn't. We're not neglecting the reluctance of the gap. We are counting the reluctance. What we are neglecting the leakage, which is basically, it's like, you get my point? So whatever basically air gap, magnetic field leaving the core to the surrounding air, we are neglecting this. So this is an analysis, it's not a very important.
دكتور في صوت
يا شباب اللي قاعد مشغل لي عن الزواج والطلاق وهالسوالف هذه يطفيها. يعني don't push me actually to know the person. I know him وابدا اسوي corrective actions او اعطي deductions او غيره. At least respect others during the class time. واضح اللي كان مشغل فيديو. طيب مو مشكلة. Okay. So that's why you are representing basically the circuit here.
بس دكتور بالسؤال ما ذكر لي انه نسوي نيجلكتنج للكور ريلكتنس.
neglecting leakage. بس دكتور طيب لو ما قال neglecting leakage كيف كم بيصير عندنا reluctant؟
ترى ما في صوت يا دكتور.
As one source and 2 reluctances for the air gaps.
يا دكتور الصوت انقطع ترى ما سمعنا شيء.